Recording in
All right,
progress.
hello folks. Welcome back to our conversation about acid-base dissociation equilibrium. In our prior video, we looked at acid dissociation specifically and how the magnitude of Ka will determine whether or not an acid is strong or weak. We are going to do a very similar treatment in this video, except we are going to look at the general base dissociation. So let's just remind ourselves about our general base B dissociation in solution. So this is some base B in the presence of water, establishing a dissociation equilibrium. Our substance is a base because it acts as a Bronsted-Lowry base, meaning it is accepting a proton from another substance in reaction. And the substance that can donate a proton is the water. So the water here is going to act as an acid, donating or protonating our base B. And once that water has lost one of its H pluses, it leaves behind the basic particle hydroxide. This is our weak base dissociation. So just like we did with our weak acid, we can define an equilibrium constant that is unique to our base dissociation equilibrium, called the base dissociation constant. And this is, again, an equilibrium constant, so we're using capital K, but this now has the subscript of B to indicate that we are looking at a base. So I'm going to stick with our general base formula. So for some general base B, if I were to write an equilibrium expression from this dissociation equilibrium that's shown here, just like with any other equilibrium expression, this would be the concentration of my products. Here, my dissociation products. So concentration of BH plus times concentration of hydroxide over the concentration of any aqueous reactants. In this case, this is our undissociated molecular base B. Where again, all of these concentrations are the concentrations once we have achieved our dissociation equilibrium. And we know from our example with our weak acid that this is going to determine whether we are strong or weak, or whether we favor the production of our basic particle hydroxide based on the magnitude of K. So Kb, if Kb is small, then dissociation products are not favored at equilibrium. So we would probably call this a weak base because it contributes very little hydroxide to the solution upon dissociation. And if this dissociation constant is large, then the dissociation products are indeed favored at equilibrium. So we would characterize this as a strong, or at least relatively strong, stronger base than something with a smaller Kb. So again, discussing acid-base strength requires us to understand the magnitude of the dissociation constant that is unique to each species dissociating. So let's look at a practice problem. So base dissociation constant, practice. So here I am given the bicarbonate ion. So the bicarbonate ion does act as a Bronsted-Lowry base when it is in water. And it has a very, very, very small base dissociation constant, or KB, of 1.995 times 10 to the negative 8. And I ask here, what is the predicted percent dissociation for this solution? So what on earth does that mean? Let's try to figure it out. What is the predicted percent dissociation? This is us asking, at equilibrium, so once we've achieved our dissociative equilibrium state, what percent of the original HCO3 minus has dissociated to form or contribute hydroxide ion in solution? And some important information here. Let's say that the concentration of bicarbonate is 0.350 molar. Okay, at equilibrium, what quantity? Ice table. So let's write out our dissociation equilibrium for the bicarbonate ion. So that is H2, sorry, HCO3. Surrounded by water. This will establish a dissociation equilibrium where the water is going to protonate our weak base. So this is going to become H2CO3. And then that will leave behind hydroxide. Okay, let's set up an ice table. Initially, before this dissociation in water occurs, the original concentration of the bicarbonate ion is 0.350 molar. Water, again, is kind of like not counted. And pre-dissociation, we have no dissociation product. So we do not expect to see our protonated product nor our acidic base particle, the hydroxide ion, present in the beaker before any dissociation occurs. And since this equilibrium is a one-to-one dissociation stoichiometry, we know that there's a decrease X in the concentration of the bicarbonate ion to achieve equilibrium. That corresponds with the same proportional increase X in the amount of H2CO3 and hydroxide, meaning at equilibrium, 0.350 minus X molar is our equilibrium concentration of the bicarbonate ion. And we have now generated X molar of H2CO3 and what we care about, X molar of hydroxide. So if we can figure out X, then we can figure out the amount of hydroxide. So let's look at our KB expression. KB has a value given to us, 1.995 times 10 to the negative 8. And this is going to be equal to products over reactants. Products here are dissociation products, so concentration hydroxide times concentration H2CO3 over concentration HCO3. All of these are our equilibrium concentrations. So I've got X times X, or X squared, in the numerator over our equilibrium concentration, which is 0.350 minus X molar, in the denominator. And let's analyze if we can apply the small x approximation here. So KB is incredibly vastly tiny, right? 10 to the negative 8. So we are going to assume that compared to the original concentration of base in solution pre-dissociation, that this change is going to be pretty negligible to get to equilibrium. So this is our, again, small x approximation. So this is equal to x squared over 0.350. And again, that's equal to 1.995 times 10 to the negative 8. This means that x is equal to the square root of 0.350 times RKB, 1.995 times 10 to the negative 8. So let's figure out what that is. So 1.995 times 10 to the negative 8 times our 0.350 molar, which is our approximate equilibrium concentration of HCO3. And then raise that to the 1/2 power, or take the square root. I get x is equal to 8.356 times 10 to the negative 5 molar. And while we do, in fact, now have our value of x, in other words, our concentration of hydroxide, still haven't answered this question, because this question is requiring us to find the percent dissociation. So how much of the original pre-dissociation amount of bicarbonate has now become hydroxide? So then percent dissociation is going to be the 8.356 times 10 to the negative 5 molar hydroxide that was generated as a result of the dissociation over the 0.350 molar original concentration that was not dissociated times 100%. This is going to be, as you can probably predict, very, very small, but let's figure out what it is. Yeah, very small percent. Check my math, but I get something like 0.024% dissociation. And it does make sense that this would be a very small amount of hydroxide percentage-wise in the solution after dissociation, because again, think about our equilibrium constant, in this case, our dissociation constant, 10 to the negative 8, very, very small, right? So this is not an equilibrium dissociation, or dissociation equilibrium, I should say, that favors the production of hydroxide. We would expect to find more bicarbonate ion present in solution than we would hydroxide, by an overwhelming kind of like magnitude. All right, so these equilibrium dissociation constants are the exact same kind of descriptors of our general equilibrium constants. They're just now applied to like a specific context of whether we're looking at an acid dissociating or a base dissociating. And so far, when we've looked at these values, these Ka and Kb values, we're still in the land of like, what happens if I were to throw this acid or throw this base in water, right? We're thinking about what happens if I've just got a solution of, say, acetic acid in front of me. What happens if I have a solution of ammonia in front of me, right? what is going on? What can I say about the amount of acid or base particles present when that solution exists in its dissociative equilibrium state? Coming up, we're going to talk about pH. We've talked about pH a little bit in lab already, so I've given you kind of like a Gen Chem 1 definition of pH. And we are going to still use that definition if we're talking about just like a beaker full of acid and or a beaker full of base. However, when we start reacting acids and bases together, as we've been doing when we do these titration curves, that's when we have to start thinking about something a little more nuanced. So let's have our conversations about pH, and then after that, buffers in our next series of videos. So see you then.